Hello everyone, how are you? How's everything? So today I'm going to continue telling you about the Laplace transform and we're going to learn some new cool things about it. So last session we ended up learning that taking a function from time domain to Laplace domain is simply possible using this formula, the integral of 0 to infinity of f of t to the power of minus st dt. Also, you remember that I told you that you will never need to use this formula as you always have a table that is actually giving you the main Laplace transforms that you need. For example, I'm going to show you a few of the most useful ones, like for example the Laplacian of ut is 1 over s. This one we actually use the formula to prove that this is the answer. The Laplacian of rt is 1 over s square. The Laplacian of t square ut is 2 over s cube. Or the Laplacian of any t to the power of n times ut will be n factorial over s to the power of n plus n. So you will have a table, a complete table that any possible function that you're dealing with is listed there with its Laplace transform. But I'm gonna tell you about some properties of Laplace that are gonna be very useful for us to be able to transform any variety of the signals to the Laplace domain. Two main properties that I'm going to tell you about are these two: the time shift and the frequency shift. And I'm going to tell you this very simply. Imagine you have your function in time domain as ut. As we know, the Laplacian of ut is going to be 1 over s. What if my signal was shifted? Now my signal is u of t minus capital T. The Laplacian of this new function will be e to the power of minus capital Ts over s. What changed here? Before, when I had ut, my Laplacian was 1 over s. Here, this shift minus capital T just multiplied the answer by e to the power of minus capital T s. As simple as that. So if you have a shift by any value, if you have a shift by a, for example, if you have u of t minus a, your answer will be, imagine if it is a, let me try to do it. If it's a, your answer will be e to the power of minus as over s. If this is 5, if this is 5, u of t minus 5 will be e to the power of minus 5s over s. This is simply how we apply a time shift in Laplace domain. So when you shift something by a value, you in time domain, in Laplace domain, your answer is going to be multiplied by e to the power of minus that value times s. So example, what is u of t, what is the Laplacian of u of t minus 13? Of course you can guess it's going to be e to the power of minus 13s over s. Super simple. How about the frequency shift? Frequency shift, it means that if you had in the Laplace domain, if you had a shift of a, for example, if you had a f of s plus a, it means in time domain your function had been multiplied by an exponential e to the power of minus 80. Look, they are like a duality feature. Here, when you shift something in time domain, in Laplace domain, it's being multiplied by an exponential. If you multiply by an exponential in time domain, in frequency domain, it's going to be shifted. For example, if you have e to the power of minus at times ut, your answer here is going to be f of s plus a. It means it's going to be it's going to be f of the Laplacian of ut was 1 over s. So it's going to be 1 over s plus a. Let's do it here. So let's bring this setup with us here. So we bring it here. So if I multiply this ut by e to the power of, let's say, this one, by e to the power of minus at, my answer here will become 1 over s plus a. Look, as simple as that. So e to the power of minus 80 times ut, the Laplacian will be 1 over s plus a. So if I multiply it by e to the power of minus 60 ut, so in time domain, I multiply ut by e to the power of minus 60. In frequency domain, in Laplace domain, my answer will be 1 over s plus 6. So now you can see why I said they do have like a duality feature. When I'm repeating, when I'm shifting the function in time domain by a value, in Laplace domain it's being multiplied by e to the power of that value s. If I'm multiplying in time domain, if I'm multiplying the function by e to the power of something, in s domain is going to be shifted exactly like this. The Laplacian of e to the power of minus 60 times ut will be 1 over s plus 6. And remember this example, the Laplacian of u of t minus 13 will be e to the power of minus 13s over s. Just keep something in mind, it's a little trick. When you shift in time domain, the sign will stay the same in the frequency domain, in the Laplace domain. So minus 13, minus 13. But when you multiply by e to the power of something in time domain, the sign will change here in the Laplace domain. Here we multiplied by minus 60, it became 1 over s plus 6. So this is the most, I'm telling you, these two are the most important properties that you're going to deal a lot with them. And I'm going to give you an example right now to see how cool these two simple properties can help you to find almost the Laplacian of any function. For example, imagine you want to find the Laplacian of sine of omega t ut. So in the beginning it might look a bit complicated, but I think your mind is still fresh. Let's use the Euler's formula to expand sine of omega t. The sine of omega t will be e to the power of j omega t minus e to the power of minus j omega t over 2j, right? So if my function is sine of omega t ut, it means that f of t will be these 2 times ut. So e to the power of j omega t times ut, isn't it reminding you of what I just told you right here? E to the power of something t, f of t will become f of s plus a. So e to the power of j omega t over 2j times ut, it means I'm going to have 1 over s plus a. A here is what? J omega t. J omega basically. For the other one, my a will be minus j omega. So I will end up having 1 over s minus j omega minus 1 over s plus j omega, right? And I took this common factor from 1 over 2j, I left it outside. So my function in s domain will be 1 over 2j, which I took common factor from this. For e to the power of j omega t ut, it became 1 over s minus j omega. because you remember I told you the sign will change here. So I had plus j omega here, it becomes s minus j omega. And here minus, I had minus j omega here, it will become 1 over s plus j omega. And then I can try to take a common denominator here. So I multiply these two by each other. They're like conjugate pair. So the denominator will be s square plus omega square. The denominator will be this one, goes here, s plus j omega minus s minus j omega. So s's cancel each other. So it will become 2j omega over s square plus omega square. And 2j will cancel this 2j here. So the answer will be omega over s square plus omega square. Exactly the same thing can be done for cosine of omega t. Remember the Laplacian, the Euler expansion of cosine of omega t was e to the power of j omega t over 2 plus e to the power of minus j omega t over 2, right? So again, using this property that e to the power of minus at ut will give you 1 over s plus a, here, because look, the whole thing is being multiplied by ut, right? It's like this whole thing is being multiplied by ut. That's why it's gonna be e to the power of j omega t over 2 ut plus e to the power of minus j omega 2 over 2 ut. So this first one will give us 1 over s minus j omega, because a was j omega here, the sign will switch, and the second one will become 1 over s plus j omega, and this 2 I took common factor from this 2. Then taking the common denominator will give us s square plus omega square in the denominator. Denominator will add them up, s plus j omega plus s minus j omega, then j omegas cancel each other. I will have 2s over 2 times s square plus omega square, 2's cancel each other. I will end up having s over s square plus omega square. Now I would like you to try something. I would like you to find the Laplace transform of this function 10 e to the power of minus 2t cosine of 40 ut. Look here, you have to use both properties. Actually, in a way, cosine of 40 ut, you already know the answer, right? Because in the previous example, we already figured out what is the Laplacian of cosine of omega t ut. It's going to be s over s square plus omega square. So as you can guess, cosine of 40, it means omega is 4. So it's going to be s over s square plus 16, right? So I'll just give you a hint. Then this one is multiplying the function by an exponential in time domain. So in the frequency domain, you're going to have a shift again, right? So your s will be shifted by how much? You figure it out for me, okay? So try to solve this example for me, and we'll discuss it on Thursday. Thank you very much. Have fun, take care, and we'll see you soon online.